Hi, my name is Tomasz Schulz. I am a research assistant at the Josef Stefan Institute. Our institute is one of the 8 core partners of the CREW project. The goal of the CREW project was to build a federation of wireless testbeds for experimentation with cognitive radio and other advanced radio technologies. This is a short presentation of the GAME-COG-NET experiment, which was one of the 7 experiments selected in the CREW project Open Call 3. The experiment was performed in 2014 by experimenters from Technical University of Cluj-Napoca. Josef Stefan Institute was the supporting core partner. The topic of the GAME-COG-NET experiment was transmitter power control in wireless networks. Controlling transmitter power is important because transmitting with lower power levels leads to less interference with other spectrum users. This increases overall spectrum use efficiency, which is important in unlicensed bands, where a lot of devices share a limited piece of spectrum. In many applications, energy efficiency is also important. Using less power for radio can lead to longer life for battery-powered devices. The GAME-COG-NET experiment approached the problem of power control from the standpoint of game theory. A large number of game-theoretic models for cognitive radio networks have already been published in the literature. However, only a few of those have been experimentally validated. Many proposed models make unrealistic assumptions about practical hardware. One specific problem with existing models that GAME-COG-NET addressed was the fact that many practical radios can only transmit with certain discrete power levels. Theoretical models typically assume that the transmitter power can be varied in a continuous fashion. The focus of the GAME-COG-NET experiment was machine-to-machine communications in wireless sensor networks. This work was based on previous work done at the Josef Stefan Institute on the proactive power update algorithm. The GAME-COG-NET experiment proposed a new theoretical model for a cognitive radio network. A distributed algorithm for transmitter power control was derived from the model and validated at the CREW testbed at the Josef Stefan Institute campus in Ljubljana, Slovenia. Theoretical predictions were compared with results of practical experiments. This is a brief overview of the game-theoretic model used in the experiment. Wireless nodes in a network are divided into transmitter-receiver pairs. Each such pair is considered a player in a game. The goal of each player I is to maximize its utility function UI. The utility function is composed of a sum of 2 terms. The first term is derived from the Shannon-Hartley channel capacity theorem. Its purpose is to define players' desire for a high signal-to-noise ratio and hence high bandwidth of the channel between the player's transmitter and receiver. The second term defines the cost of power. It contains a weight factor Ci, which sets the desired compromise between channel capacity and power usage. In the GAME-COG-NET experiment, the cost term was dynamically updated each round of the game using the displayed formula. The cost update formula contains a constant parameter alpha I. Alpha I has a similar role as a constant weight factor in game models with a static cost of power. Performance of the proposed algorithm in indoor environments was tested in an office at the Josef Stefan Institute campus. 8 Vesna sensor nodes were installed at the locations shown. Each Vesna sensor node was equipped with a narrow-band radio operating at 2.4 GHz. One pair of sensor nodes formed one player in the game, hence the game had up to 4 players. The office was in normal use during the experiment. The proposed algorithm was also tested in an outdoor environment. For this purpose, 8 Vesna sensor nodes were placed on buildings surrounding a small park at the center of the Josef Stefan Institute campus. Except for trees growing in the park, the nodes had direct line of sight with each other. The park experienced some light motor vehicle and pedestrian traffic during the experiment. Again, sensor nodes were equipped with narrow band radios operating at 2.4 GHz. The proposed power update algorithm requires knowledge of direct and cross-channel gains. Direct gain is the gain between the receiver and transmitter for a single player. Cross gain is the gain between a player's own receiver and other players' transmitters in the network. Using the Vesna nodes, one channel measurement took between 5 and 7 seconds. The measured gains varied considerably over time, even in an office environment with minimal movement. Some example gain measurements for a two-player scenario are shown here. On both graphs, the red line shows direct gain and the blue line shows cross gain. Time is on the horizontal axis. Using the proposed algorithm, these variations in gain did not result in significant variations in transmitter power and were not problematic. To estimate interference between players, two methods were tested in the experiment. The first method was to measure the channel gains as mentioned previously. The interference was then calculated theoretically as a sum of products between channel gains and individual player transmission powers. The second method was to measure the interference directly as detected power at the antenna of a player's receiver, while all other players are actively transmitting. Theoretically, these two methods should give the same results. However, in the experiment, the game progressed slightly differently depending on which method was used. The progress of games with two players are shown here. On both graphs, equilibrium transmit power for player 1 in dBm is on the horizontal axis, and equilibrium transmit power for player 2 in dBm is on the vertical axis. Each point on the graph shows the result of one game. Several games were played using different values for the alpha parameter. Games on the left graph use the first interference estimation method, while the games on the right use the second method. You can see that the two methods yielded different results. This difference was not sufficiently explained during the experiment. The basic contribution of the GAME-COG-NET experiment was dynamic cost adaptation. Time progress of two games is shown here. On both graphs, time is on the horizontal axis. Transmitter power for two game players is shown on the vertical axis in dBm. The game on the left was played without cost adaptation. Because Vesna sensor nodes only support setting the power level to a discrete set of values, the game does not reach an equilibrium. Instead, players oscillate between power levels. These variations can be much higher than shown here and can lead to inefficient use of spectrum and variations in the quality of radio link. The game on the right was played with dynamic power update algorithm. You can see that a stable state is reached in just a few turns of the game. Larger games with up to 4 players were also tested in indoor and outdoor environments at the Jožef Stefan Institute campus. One of the goals was to verify the effect of the alpha parameter on the progress of the game. Theory says that alpha should define the trade-off between power efficiency and signal-to-noise ratio. With higher alpha values, the game should converge to lower transmission power. The graphs shown here show equilibrium conditions for games with 2 and 3 players and different alpha values. The axes again show the transmission power of players in dBm. You can see that in both cases players converged to lower powers when alpha was set to a high value. Speed of convergence was also tested. Many repetitions were performed with different values of alpha. This overview shows how convergence happens with different values of alpha in a two-player game. On average, players reached a stable state in 2 iterations. In a real use case, nodes often join and leave the network. This corresponds to players entering and leaving the game. A good power update algorithm should be able to rapidly respond to such changes. In this demonstration, a game with 4 players is shown, where the number of players change over time. Here, time is shown on the horizontal axis and transmitter power for all players is shown on the vertical axis in dBm. After an initial equilibrium is reached, player 4 leaves the game. The distributed algorithm detects that the interference level to player 3 has dropped and lowers its transmit power accordingly. With less interference, a lower transmit power is necessary to keep the same signal-to-noise ratio. When player 4 rejoins the game, transmit power of player 3 returns to its previous level. When players 3 and 4 leave, interference to remaining two players drops even further. The algorithm quickly adjusts their transmitter powers. For the complete GAME-COG-NET experiment, 65 hours in total were reserved on the testbeds involved. First and last reservations were 45 days apart. Approximately 100 individual experiments were performed on the testbed with average duration of 30 minutes. 8 sensor nodes were used in total. This has been a short presentation of the GAME-COG-NET experiment. For more information on the CREW project, please visit the project website at www.crewproject.eu.